Howdy. Howdy. Spicy pepper in the house. Oh, BRB, I'm going to wait for some more people to join up. Greetings. All right, I think I'm going to go ahead and start talking. A couple of announcements. First of all, I have to move my office hours today to 4:30 to 5:30 because I made plans to go out to lunch, and so I would be late to office hours. Um, so I hope that's not too big of an inconvenience. The second thing I wanted to say is that for the next week, there is a high probability that I will have to move my office hours around because my parents are visiting and they're arriving tomorrow. So, I just hope you can be flexible. I'm trying to be flexible so that I can actually spend time with them while they're here. So I don't know that I'm going to have to move it, but I may have to move it. And I'll definitely try to show you guys my parents' two dogs, Poppy and Checkers, while they're here. And then the third thing I wanted to say is that I put on the Canvas page below the all the buttons on the Canvas page. I put the AP join codes if you want to take either of the AP Physics C exams. Okay, so you need the join codes. And I'm sorry, I'm a little bit late posting that stuff. Okay, so I think I'm going to get to my lesson now. All right. So today we are going to be talking about what I like to call multi-part systems. And all that is systems with more than one piece. And so the key idea with multi-part systems is that anytime you have two objects and they're exerting a force on each other, those forces are related by Newton's third law. So Newton's third law is going to be critically important because, if thing one exerts on thing two a force of 10 newtons to the right, then thing two exerts on thing one a force of 10 newtons to the left. So we have to keep in mind Newton's third law, okay? So I'm just going to write Newton's third law is key. All right, so we're just going to do some examples. We're going to do 2 examples today, and they're kind of involved, so it should take most of the time. Okay, so both of these examples are going to be stacked blocks. All right. So let's suppose I have a floor. The floor is frictionless. Okay. And then there is a block that is, let's say, 3 kilograms. All right. And then there is a block that is 5 kilograms on top of that. All right. And there is a coefficient of kinetic friction between the 2 blocks. Okay. There is mu sub k equals 0.1. All right. And then there is a force, a diagonal force that's pulling only on the top block. Okay. And it is a, let's say, 100 Newton force that is at an angle of 40 degrees. Okay? Now here's the thing. These 2 blocks are going to have different accelerations. Okay? One block is sliding against the other. They're going to have different accelerations. And so what I want to do is I want to figure out what is the acceleration of each block. We are going to assume that there is kinetic friction between the 2 blocks. Okay, so that the 5 kilogram block is sliding across the top of the 3 kilogram block, and we're going to calculate their accelerations while they're on top of each other, because obviously if they're accelerating relative to each other, then there's eventually one's going to slip off the top of the other and hit the ground. So we're only concerned, what are the accelerations at this particular moment that is shown? Okay. This 100 Newton force is diagonal, so anytime you have a diagonal force, you want to use sines and cosines to calculate the vertical and horizontal components. So 100 sine of 40 is, let's see that, 100 sine of 40 is going to be the vertical component, so that's about 64 newtons. And 100 cosine of 40 is going to be the horizontal component, which is about 77 newtons. Okay? So we are going to do a free body diagram of the forces on each block. Okay? So let's start off with the 5 kilogram block. The 5 kilogram block has its a lot of forces acting on it. Okay? It's got the 100 Newton force. We're going to think of the 100 Newton force as a 64 Newton force going up. Hang on. Can I change the weight of the block to 7 kilograms? Okay, 7 kilograms. The thing about these problems is that you can end up with sort of contradictions if you don't set up the problem correctly. So I accidentally set it up so that it has a contradiction. I apologize. We're going to make that 7 kilograms. Okay? Because if you have a 64 Newton upward force on a 5 kilogram block, that would actually lift the block up off the top. So yeah, so I'm going to make that 7 kilograms so that the downward force from weight is 70 newtons. Okay? And then this is a 77 Newton force to the right. Okay? We've got a normal force from the 3 kilogram block, and I'm going to call that N sub BB. Why am I calling it NBB? For between the blocks. Okay, NBB for between the blocks. And then the interblock friction is going to be acting to slow down the 7 kilogram block, right? Because the 100 Newton force is pulling the block to the right. And friction says, no, 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 don't move. So friction is going to actually hold the 7 kilogram block back. So there's a friction force going to the left. Okay? So those are the forces acting on the 5 kilogram block, or the 7 kilogram block, my bad. 7 kilogram, 7 kilogram. Okay. Now let's do the 3 kilogram block. All right, and we're going to use Newton's third law. So the 3 kilogram block does not have any of this business of the 100 Newton force. Why? Because the 100 Newton force is acting on the 7 kilogram block. Okay, so what we're going to have, all right, is you're going to have a normal force between the blocks, but that is going to go downward. Why is that? Well, because the normal force points upward on the 7 kilogram block, so therefore the interblock normal force is going to point downward on the 3 kilogram block, right? If I set something on my head, the normal force from the calculator pushes down on my head, all right? But then the block is also in contact with the floor. So there is a second normal force from the floor, which points upward. I will call that N sub F for floor. All right. And then the 3 kilogram block also has its weight force. Okay. So that would be 30 newtons. And then the 3 kilogram block also has friction. But friction is actually pulling the 3 kilogram block to the right. Okay? Why is that? Well, if I, here I have a piece of cardboard and I put my calculator on top of it. If I pull, wow, this is a really slippery calculator. Let's say I put my phone on top of it. If I pull, the heck, okay, there we go. You see how if I pull the calculator, it actually brings the piece of cardboard underneath it along with it due to friction, okay? So friction is actually pulling the 3 kilogram block along to the right, okay? So now what I have to do is I have to use Newton's third law to connect the action-reaction pairs, okay? Notice how the normal force between the blocks must be equal in size because those are action and reaction. The friction forces must be the same size because those are an action-reaction pair. Nothing else is an action-reaction pair in this problem. So, all right. So now we're going to go to Newton's second law. Okay. We're going to write Newton's second law in the x direction and in the y direction for each block. Okay? So Newton's second law in the y direction is going to be net force. So the net force in the y direction is up forces minus down forces. So NBB plus 64 minus 70 equals, now what is the acceleration in the vertical direction? It's going to be 0 because the 7 kilogram block isn't lifting up off the top of the other block. Okay, so that's 0. The forces in the x direction are right forces minus left forces, so 77 minus friction, and that equals 7 times the acceleration of the 7 kilogram block. Okay, so that's a horizontal version of Newton's second law. All right, then if we look at the 3 kilogram block, in the vertical direction, it has an upward normal force. It has a downward normal force between the blocks, and it has a downward weight force. And that has to equal 0 because the 3 kilogram block is pinned to the floor. Okay. And in the x direction, all we have is friction. So friction equals 3 times the acceleration of the 3 kilogram object. So we actually have, let's see, we've got 1 unknown, 2 unknowns, 3 unknowns, 4 unknowns, 5 unknowns. So we actually have 5 unknowns here that we're going to end up solving for. So right away I see the y equation is for the 7 kilogram block is very simple. It says that the normal force between the blocks is 6 newtons. Boom. So there we go. Now that's going to allow us to calculate the friction between the blocks. Why is that? Well, the friction between the blocks is equal to mu times the normal force between the blocks. Okay? So we're not going to use the normal force from the floor because there is no friction with the floor. Okay? We're going to use the normal force between the blocks because that's where the friction is. All right? So the friction force is going to be 0.1 times 6. So it's 0.6 newtons is friction. Okay? So now that's going to allow me to plug in here and here for the friction. So I have, so that's friction. So I have 77 minus 0.6 equals 7 times the acceleration of the 7 kilogram block. That's a simple linear equation, which I will solve without showing the algebra. So 76.4 divided by 7, that's an acceleration of 10.9 meters per second squared is the acceleration of the 7 kilogram block. Boom. Okay. Plugging that into this equation gives 0.6 equals 3 times a sub 3. And that tells me that it is 0.2 meters per second squared is the acceleration of the third block. I know that the normal force between the blocks is 6 newtons. So that says that the normal force from the floor is 36 newtons. Okay. So I have solved for all the unknowns and I've completely specified what is going to happen in this situation. All right? So that's an example of a multi-part system. They're kind of fun. You do have to be careful though, because you can get into situations where you get contradictions, as I almost did. So for today's quiz, I have tried to write it so that there are no contradictions, but I can't guarantee that I succeeded, so hopefully I didn't. But maybe I did have a contradiction somewhere, so I'm sure someone will send me a message if there is a contradiction. Okay. Let's do a second example. Let's suppose that we have two blocks on top of each other again. We have a floor. Okay. And this is let's say a 2 kilogram block. And this is a 1 kilogram block. There is a coefficient of friction with the floor that is 0.3. And there's a coefficient of friction between the blocks that is different. It is 0.2. Someone pulls on the bottom block with a horizontal force of 100 newtons. And once again, we want to figure out what are the accelerations involved here. So this is very similar to, have you ever seen that trick that people do where they have, they have two things on top of each other and then they yank out the bottom thing like that. Okay, so I've got a big force on the bottom thing that's going to cause the bottom thing to have a huge acceleration. And notice how the top thing is going to move a little bit, but not very much because it doesn't have as much of an acceleration. So like that. All right, so this is basically the problem that we're trying to solve. I'm going to start off with drawing a free body diagram for the 1 kilogram object and for the 2 kilogram object. Okay. So for the 1 kilogram object, it has a normal force from between the blocks, N sub BB. Okay, the 1 kilogram block is not in contact with the floor, so it doesn't get a normal force from the floor. It only gets a normal force between the blocks. We have got a weight force, which is going to be M times G, or 10 newtons. And then if we think about it, the 2 kilogram block is going to start sliding to the right, which is going to pull the 1 kilogram block along with it. So the frictional force between the blocks, I'll call it F sub BB, is going to point to the right for the 1 kilogram block. Okay? I'm giving that a subscript this time because there's also going to be a friction force from the floor because it has a non-zero coefficient of friction. All right? So now let's look at the 2 kilogram block. The 2 kilogram is more complicated. It has the 100 Newton force pulling on it to the right. Okay. It has the friction between the blocks holding it back. These two forces are action-reaction pairs, so they have to have the same size. So I'm going to put a slash there to indicate they have the same size. We also have the friction from the floor. So I'll call that F sub F, or all right. The 2 kilogram block is being pushed down by the block above it. So there's going to be a downward normal force between the blocks on the 2 kilogram block. And this force is an action-reaction pair with that force. So those two have to have the same size. Okay, so I'll put double slash to indicate that these two are equal, but not necessarily the same thing as those two. And then we also have a normal force from the floor. Okay. So now what we want to do is we want to do Newton's second law in the x direction and in the y direction for each of these blocks. So in the x direction for the 1 kilogram block, it's very simple. We only have friction. So we have F sub BB equals 1 times the acceleration of the 1 kilogram block. In the vertical direction, we have normal force between the blocks going up, and we have weight force going down, and that has to equal 0 because the 1 kilogram block is moving side to side, not up and down. For the 2 kilogram block, the x direction, we have 100 Newton force going to the right, and then we have 2 friction forces going to the left. So we have 100 minus FBB minus equals 2 times the acceleration of the 2 kilogram block. That's Newton's second law for that. In the y direction, we have 2 forces. Oh, I forgot one of the forces. There's the 20 Newton weight force going downward on the 2 kilogram block. How come no one said that? Come on, you're supposed to let me know if I make a mistake. So I have N sub F going upward, and then I have normal force between the blocks and 20 going down. And that equals 0 because the 2 kilogram block is only moving side to side. So now I got to solve all these equations. Okay, this one I can see is really simple. It just says normal force between the blocks is 10 newtons. Okay, so this is 10 newtons. This is 10 newtons. Which is going to, in turn, tell me friction between the blocks. Friction between the blocks is equal to the coefficient of friction between the blocks times the normal force between the blocks. Coefficient of friction between the blocks is 0.2. Normal force between the blocks is 10. So we have 0.2 times 10, which equals 2 newtons, is the frictional force between the blocks. So that means I can write this as 2 newtons, and that means I can write this as 2 newtons because it's an action-reaction pair. That's going to then allow me to solve for the acceleration of the top block. It's going to be 2 equals 1 times a sub 1, which says that the acceleration of the top block is 2 meters per second squared. All right. Now I'm going to go to this equation right here. All right. I just found that the normal force between the blocks is 10 newtons. So that tells me, so we have n sub f minus 10 minus 20 equals 0, which says the normal force from the floor is 30 newtons. If I know the normal force from the floor, then I know the friction from the floor. Okay? The friction from the floor is going to be the coefficient of friction with the floor times the normal force from the floor. So that's going to be 0.3 times 30. Okay? So that equals 9 newtons is friction from the floor. So now I know friction between the blocks and I know friction from the floor. Okay? So friction between the blocks was calculated to be 2 newtons. Friction from the floor was calculated to be 9 newtons. And that equals 2a sub 2. So that tells me that 89 equals 2a sub 2. So solving that equation gives me what, 44.5 meters per second squared equals the acceleration of the second block. Okay, so this is an introduction to multi-part systems. Again, I want to stress that you can get into some contradictions if you're not careful. So in these examples that I did, it was fairly obvious which direction friction was going to point. Sometimes it might not be obvious. Sometimes you might have static friction and not kinetic friction, so it can get really tricky. If you had 3 or 4 objects, then you would have a lot of free body diagrams and a lot of equations. So I'm going to stick to just 2 objects. So that's my lesson for today, and I will see you in the Zoom room.